chromatic point, corresponding point in this two-dimensional space to hue. That means if you consider this is the origin, so if you get a vector, the direction will give you the hue and the corresponding radius will give you the saturation. So this is one thumb rule by which you can represent saturation in a 6-dimension. Now, color reproducibility, I was mentioning that all colors are not reproducible from a set of primers. So there are certain set of colors only reproducible, and this is what is known as color gamut. So if we look at these vertices in the chromatic space, they are the representation of the corresponding primary color. Now, linear combination of all these primary colors will give you the corresponding color. That's the additive model. So if it's a linear combination, that you understand that it becomes a convex segment, it's a triangle. So it has to be a triangle, and so whatever color is there within this triangle, those are reproducible with this set of primers. So if you would like to have a different different color gamut, so you have to change your primers. So this is what is interesting. So this is an example. So by taking different primary colors, set of primary colors, you have different types of gamuts. And in fact, if you have multiple sources with more number of we should say some auxiliary points in the color space also, you can increase this color gamut, and you can have more color reproducibility. So that is also the technical, as you can see, that multiple level source for DSP projectors. So for different kind of projections, this color gamut system. When you are processing color, so now you have the option of different color spaces, as you can see that originally started with RGB, that is the our sensors, they work in the RGB color space. You have the red, green, blue filter, and you get the red, green, blue components. But finally, we see that processing in the RGB color space is not very convenient, because RGB is not directly related with our color perception. So we need different kind of perception model, and there are different models for that, for different purposes. Now, in the compression space, already it has been you know that, and also Shantu mentioned it, that actually we have this complementary blue and complementary red, this YCB here color space, which is used. After experimenting, they have found that it has very, it can in fact reduce redundancy to a great extent. That is one concern of compression. So we would like to decorrelate the color components to the greatest possible. Of course, there are theoretically there are other spaces where color decorrelation is much more, but still this space is good. So this is the example of this conversion. You can see that actually, though you could have transformed. You could have represented this transformation into a linear transformation, but it's not linear. You see that there is a scaling, there is a translation term, just to make the dynamic range from 0 to 255. So that because it is designed with respect for the purpose of compression, where you are trying to handle taking all the values between 0 to 255. So that is why this transformation is designed. And this you should note, because in the compressed domain, when you are processing color, actually you will be processing color. You are not processing color in the red, green, and blue zone. And this is one particular characteristic, that transformation from RGB to YCB here is not really linear. Okay? There is a translation curve. So you have to take care of that to make it. So with this introduction, I would just give an example of, in fact, I will discuss about two particular type of processing in the colors, for colors. One is for enhancement, and another one is for color constancy process. So let me first discuss about this enhancement, color enhancement thing. So enhancement, you all understand that image enhancement is meant for actually to increase our visual perception. to increase contrast or to have the right amount of contrast, brightness, and also the colors, so that we can perceive that image better than what it is. So there are different approaches for enhancement. Like some enhancement uses DC coefficients for increasing brightness, because DC coefficients, they capture the background illumination of a block. So if you increase the DC coefficient value or decrease or modify it, so you can also change the local contrast of this background. Some algorithms also consider the AC coefficients, which are more measures towards the contrast for doing these things. And a combination of both, of course, in some we try to with the colors. Now, one of these methods, one of these methods, it employs this exact. Yeah. This is basically this equation. Anyway, the idea is that when you are doing DC coefficients, I understand that you must be knowing about the gray level enhancement technique. It's basically pixel transformation. So you have a monotonic function, and in a monotonic, if you use a monotonic function, so what you are trying to do, you are trying to increase the dynamic range of the brightness value in a gray level image. You are increasing the dynamic range, and by increasing the dynamic range, you are trying to increase the visibility or contrast of it. So similar thing you can do, just first you can modify the DC coefficients using that kind of monotonic function. So in all the plots you have that advantage, and then after that, so that part is not mentioned here. After doing that, actually then you process AC coefficients. You modify the AC coefficients to increase the contrast. I will give you an example of an approach which we have adopted here using similar concepts. Like we have identified there are 6 tasks in this process. Like one task is the background illumination. You have to adjust the background illumination, and we can use the DC coefficients of the Y component. You can preserve the local contrast. Like you can scale AC coefficients of the Y component appropriately.